please join me in welcoming Paul Zeitz.
Hi, everybody. I'm glad to be here, and I'm sad that I'm no longer in New York, but I'm also relieved that I'm no longer in New York. I'm back at home in California, and I hope to be able to come back to the museum as soon as it's open. I've been working with a group of high school kids on Sunday afternoons, and we have a little pool going, a betting pool on when the museum will open, and the person who predicts closest to the opening date will get a prize. And I just think that's, you know, a fun thing to think about. Anyway, I have my virtual background, so it's as if I'm standing in front of the museum on 26th Street now. What I usually do when we're doing this in person is I have a slideshow, and so I'm you know, advancing slides from my computer with a clicker, and then we're talking and people can interrupt with questions. The interrupting with questions part might be a little tricky. I guess there's the, why don't we experiment just for a second? Could somebody, let's see, could Sarah Munchin raise her hand? Can you raise a virtual hand? Is there a way to do that with your computer?
Yes, I have to find it.
Okay. There
it is.
There it is. Okay. And my problem is I probably won't be able to see everybody's hand because I don't see, I have it configured so that I'm not seeing all of people's.
Paul, if you click on the Manage Participants,
yeah,
then you'll be able to see the blue hands in the chat window.
In the chat window.
It's very easy to scroll up and down and see those. And I think actually the blue hand, when someone raises it, it brings their name up to the top.
I didn't see, could you do that? I see the blue hand on your video screen, but I don't see the blue hand on in the chat.
So go above the chat. So you have to click on participants, or manage participants.
Participants.
Yeah. Oh, I see. Oh, yeah. I see a bunch of blue hands. Yeah, I see what you mean. Yeah.
So when someone raises their blue hand, their name will come up to the top of that.
Oh, yeah, yeah. Oh, I see all the. Okay, very interesting. Yeah, I see Lynn, Sylvia. Yeah. Okay, great. Okay, can you lower your hands now? That would be good. All right, good. Yeah, okay. And if that doesn't work, it appears that people are able to unmute themselves and they can just shout and ask a question. I ask you mostly to not do that. Yes, Sarah?
We can actually ask questions via chat.
Yes, but right, and that is only good if I'm paying attention to chat.
Yes.
And generally, if you're going to ask a question, it should be a public question.
Okay.
And then so that everybody can hear it and we can discuss it. So, and I will stop from time to time to say, are there any questions too? All right. Well, why don't we get started? So I'm going to go to my slideshow, and I might occasionally use a Blackboard as well. So you should be able to see something that says Statistics for Citizens Part 4. And the way I have my screen right now, I'm not seeing anything but my slideshow. So if you need to interrupt me, then you'll want to probably, you know, if there's an emergency or something, then interrupt. But so this is part 4 of what was a 3-part series that ended in February, and it was called Statistics for Citizens. And the goal was just to go over basic ideas of statistics so that you could be a good citizen and read the newspaper and understand things, especially like political polling. And when I finished session 3, I realized that I should have had a 4th session because I never got to one topic that I thought was important, which is linear regression. And so that's what this is devoted to. Now, if you hadn't been to the first 3 sessions, you, depending on how rusty you are, you might have a little trouble with some of the concepts, but there is a document that summarizes the first 3 sessions, and that I think was distributed to you. And after this, I will make a newer summary that puts all 4 together. And I also have some references. And at the end of the talk, I have my email address, so you can reach me with questions. Okay, so the idea of I want to briefly sort of review what we did earlier in the mini course, but the main goal for today is just 3 things: the idea of bivariate data, understanding 2 variables, and 2 computational things that allow us to think about that. One is called the correlation coefficient, the other is called the regression line, or the least squares line. And I always started my things with this silly Wikipedia quote: "What is statistics?"
The list again, or not yet?
Say that again. I could not hear that. Oh, all right. And so in our first session, we went over percentages and talked about the meaning of probability, and we looked at some notions to try to understand just simple proportions and probability, just to get comfortable with sort of numerical reasoning. And we were able to I think do some interesting paradoxes, including Simpson's paradox, and how to think about conditional probability. And then in the second session, we introduced the idea of random variables, variation, mean value, expected value, and how you measure variation with standard deviation and other quantities. And in the third session, and we also developed the idea of the normal distribution, and the all-important idea of a z-score, which I will be reviewing later today because we're going to use that. But the basic idea of a z-score is if you have a variable that has, it doesn't even have to have a normal distribution, but in general, if it has a normal distribution, a bell curve distribution, one way of describing values of the variable is not the actual number, but how many standard deviations you are above or below the mean. And so if you look at American male height, where the mean is 70 inches and the standard deviation is 3 inches, someone who's 5'7" has a z-score of -1, and someone who's 6'8" has a z-score of about 3 1/3. So, and we will use the concept of z-scores. They're very important and they're very intuitive once you get used to it. And in the third session, we just dove deeply into the central limit theorem, and we tried to understand how polling works and how confidence intervals work, and the idea of statistical significance. But now we are wrapping things up with the idea of linear regression, and the idea is, what do you do when you have 2 variables? And so what we'll first do is look at a lot of graphs, get a sense of how these graphs are working, and then we'll learn how to do some very basic computations with them. I have a computer demo for you with a link to how to use it, and most of what we're doing won't have a lot of calculation, and I want to end mostly with a lot of caveats, because statistics is very easy to do. Any idiot with a computer can do statistics. In fact, if you're like me and you're a nerd, you're probably making silly charts of coronavirus stuff because there's tons of data. And it's silly because the data is bad. And so if you have bad data, you can do really good computer crunching of bad data, and it's, as long as it's just a hobby, it's fine. But when you start making pronouncements, then you get into trouble. And a lot of things go wrong when people do statistics with either bad data or even with good data, but then they don't really understand what the statistics are telling you. And so we'll really end with the sense that we understand less than we think we do, and mathematics, at least in this arena, is not necessarily as powerful a tool as some people might make it out to be. So I want to really end on a sort of a critical thinking note. Okay, so the idea of the stuff we're doing here is we need 2 variables. So whenever you have like 2 different measurements, like height and weight, you can always try to understand the relationship between those 2 variables. and you just draw a plot. The X values we call the independent variables, and the Y values we usually call the dependent variables. And sometimes we'll call the X value the explainer and the Y value the response. And you'll see why. So I spent about 10 minutes just finding things online, just to get a variety of, and then I built some examples of my own, because I wanted you to see some real data. And so this is a good example of a scatter plot that also uses color to indicate some things. Oh, somebody is annotating, and I need to not allow that. So disable attendee annotation. Okay, and there we go. Okay. So I'm sure that, somebody just did that by accident. So here we have a, unless I did it, it's possible I did it myself. So this is a graph that is displaying, has two axes. Life expectancy is on one and healthcare expenditures on the other. And the population is countries, individual countries. And so each country has two coordinates. So Switzerland, its life expectancy is about 83, and its health expenditure is about 70, probably billions of dollars or something, or $70 per person. Yeah, I guess it's $70 per person, something like that. And so what you can see is if you move in this direction, you are moving in the direction of longer life. And if you move in this direction, you're moving in the direction of bigger expense. And most of the countries seem to fit a pattern that the more money you spend, the longer you live. That Latvia doesn't spend as much and they don't live as long. Switzerland spends a lot and they live more. And everything looks pretty nice except for an outlier, which is the United States. And you can see the United States spends more than anybody, but for some reason, the life expectancy yield is less good. Okay. So this is a good example of a public health scatter plot. And here's another public health one. And this was each of the individual dots in the scatter plot are census tract neighborhoods in the city of Boston. And somehow they were able to determine what percentage of people in each census tract smoked. And they were able to determine how much or how little activity the people had. And there seems to be, as you can see, what we call a strong positive association. The more you smoke, the more inactive you are. So it looks like a positive association. If you wanted, you could say it's a negative association. The more you smoke, the less active you are. It all depends on words. And this is a fairly interesting one. It's controversial. This comes from economics, and it was posted on a blog by a Harvard economics professor, Greg Mankiw, and he noted that this is during 20 years from 1990 to 2010, when and each of these are financial quarters. So there should be, like 40, 50 dots in here. And for each of these, it seems like when you're having more investment as a ratio of gross domestic product, there seems to be less unemployment. So you seem to have a strong negative association. This is controversial because if you included previous years, you'd see dots over here, and it sort of makes an X. But still, the scatter plot as shown for the 20 years from 1990 to 2010 seems to show a strong negative association. So these are sort of visually very powerful. Here's another true data set, which comes from a study of college students, I forget where, but college students, about 300 college students in a math class. And each dot is a student. And the x-axis is absences, and the y-axis is their score from 0 to 20 on the final exam. So this individual here hardly showed up and got a score of less than 50%. And then you see all of these students here, they had perfect attendance, yet their final exam scores ranged from quite bad to nearly perfect. And then you can see there's some students here who got perfect scores, but they also were absent a little bit. And if you look at this, it's really hard to say anything of the sort, the more you're absent, the better you do, or the more you're absent, the worse you do. It looks almost as though there's no association at all. Although when we do a computation, we will discover that there is a certain association. And here's another one that again is using real data. It's a group of young adult males. I'm pretty sure in a college, and I have a whole spreadsheet of all kinds of biological measurements. But I just took the simplest ones, namely height and weight. And what you can see is that, for example, this person here is rather short and rather light. They're 64 inches tall and about 120 pounds. And then here we have somebody who's about 6'1" and weighs about 375 pounds. Here we have a very tall person who's about 6'7" or 6" or something, and they're also weigh about 220, 230 pounds. And if you look at this and you're trying to say taller people are heavier, can you say that?
Only minor, very, not much.
It doesn't seem like there's much. Yeah, and I'm glad somebody spoke up here, because I would like some response. Can you? Because after all, if you look in here, you can find some short people who are pretty heavy. Like there's somebody who's Tom Cruise's height allegedly and is 200 pounds. And there's a bunch of people that are also short and fairly heavy. And but the question, but is there really a way to say, so here's an interesting question. Suppose all you knew about somebody was that they were a young adult male, and you knew their height. You knew that they were, say, 6'2" tall. What if you had to say what their weight would be? Obviously, there's no way you can be completely sure. But so let me use an analogy that I think I mentioned in some of the previous sessions. So suppose you are, your job, you have to guess. And you need as much information to make the best possible guess. And you will be punished by how bad your mistake is, okay? And let's make the punishment so let's say the punishment is an electric shock, and the electric shock is proportional to how bad your estimate is, but it's not just proportional to how bad it is, it's proportional to the square. The reason is because if we go back to the world that we were studying back in February, with the normally distributed random variables, everything's really close to the mean. So 95% of a normally distributed random variable lies within 2 standard deviations of the mean. And so if you have a guess that's far from the mean, it should be a guess that should have a low probability of occurring. And so you want to be penalized for outrageous guesses. So if you said a 6'2" person weighs 400 pounds, that's outrageously bad, and you should get an outrageous punishment. So the question, though, is what's the best guess that will minimize your punishment? I'm sorry to have this sort of painful approach to this, but and if you don't like punishment, you could say, okay, you get paid in chocolate chip cookies. What's the guess that gives you the minimum amount of chocolate chip cookies? Okay, it's the same idea. So here's another one, and here there's obviously a really good association, and in fact, and this is something that's well known to college professors, and it's kind of a little known, it's a dirty secret, which is after you give the first midterm, you pretty much can give the grades to your students right then and there. I mean, you don't do that; it's unethical. But take a look at this. As this is the score on the first exam between 0 and 20, and here's the score on the final, and it's not perfect. You know, like a student who got a score of 50%, some of them got below 50 on the final, and some of them did rather well. But but sort of the best student who scored 50% on the first midterm, they all of the students who aced the first midterm did better than the best student who failed that first midterm. And if somebody really failed the first midterm, like got 5 out of 20 points, then the maximum score they're getting is less than 50% on the final. And the students that got nearly perfect scores on the midterm, pretty much they didn't disappoint on the final. So even though there's a fair amount of spread in the middle, as you get out over here and over there, there's the outcomes are fairly small, and it's plausible that that a lazy college professor could just say, okay, given that you got a score of 14 on the midterm, I'm just gonna assign you a final grade based on you getting a score of what looks like about 14 on the final. It almost looks like whatever your score is on the first midterm, it's going to translate into the same score on the final. So this is an example of a very strong positive association between two variables. And again, I want to remind you, the variables are the first exam and the final exam, and the population. Each of these dots actually represents a person from whom we are taking two measurements, the measurement of their first exam and their final exam. In the other one, it was their height and weight. Same idea. Okay, and this is one I just wanted to remind you from the last example we did back in February. For those of you who were with me, we discussed the notion of whether there is selection if in heterosexual pairings, if a female has a preference for a male partner who is taller than them, and we did a sort of a what if case. What if it was random? And after men on average are taller than women, so you would predict random pairs of men and women. Most of the time, the male would be taller than the female, but you can accurately, using normal distribution, predict the probability that the female is taller than the male. And then the question is whether that would be the case in the real world. And there actually is a real world data sample, and it's something called the Millennium Cohort. It's the Millennium Cohort, and then the last word is S. Study, Millennium Cohort Study, which was it's been going on, I think, for about 20 years. And it's a longitudinal study, mostly of health in children. But when they interviewed the parents, they got as much information as possible, including heights and weights and incomes and a zillion things. So there's this wealth of data with, like, I'm not sure, at least 10,000 people in the UK. And what makes this scatter plot interesting is that it uses a grayscale coding to indicate frequency. So each dot is not a person. The little gray dots are 20 people, and the dark ones are 200 people. And so it has so you can see most of them are clustered in here, where you have average female height and average male height. But you do have things like, for example, this person here is an average height female who's paired with an unusually short male. And then you have an average height female who's paired with a tall male, and so on. And here you have, a very tall woman who's with a very tall man, and so on. There seems to be a positive association. Now, I have a subtitle, which is what is the line and what does it mean? And I will get to that later. The line is very important. We'll talk about it. The line is super important. Okay, so these are just examples of spreadsheets. And what I want to now do is find a way to quantify this idea of association. And so in order to do that, we want to focus on the notion of z-scores. And so again, I want to remind you how a z-score works. And so if x is the value of the variable, and you know that the variable has a mean, an average value of mu, and a standard deviation of sigma, and you might forget, what was sigma? Well, sigma was a weird calculation. A good way to remember sigma was that sigma basically has about the same size as what I called back in February the MAD, the MAD, which was the mean absolute deviation. So imagine you have a population, like say something like height, and you have a sample of people, maybe 1,000 people. You can work out their average height, and then for each person, you can find out how much they differ from the average height. And if it's positive, it'll be a positive number. If someone's shorter, it'll be a negative number, but you take the absolute values. And so you add up all of these deviations. So you make sure that negatives and positives are both turned into positives, so they don't neutralize each other, and you find the average. And so the standard deviation is essentially the average amount people deviate from the mean. So with things like adult height, the standard deviation tends to be about between 2 and 3 inches. And so what that means is that is that on average, if you had a large group of people and you found out how much they differed from average height, you'd find that the average difference is about 2 to 3 inches, roughly speaking. So that's really what standard deviation means. It has a complicated formula, but it has a very intuitive meaning. And so for any variable where you know the mean and you know the standard deviation, which again is really just a measure of variation of the variable, you can normalize it to compute what's called the z-score. And the way you do that is you take the number, you subtract it from the mean, and then divide by the standard deviation. I probably should have done a numerical example. And if you need one, speak up and I can turn to the blackboard and show you, but I'll just talk you through one right now. So with American male height, as I mentioned in the previous, one of the previous slides, the mean is about 70 inches, about 5'10", and the standard deviation is about 3 inches. So if somebody is say 6 inches taller than average, so that would be 76 inches, which would be, what is that, 6'4" or so? A person who's 6'4", they're 6 inches taller than average. They're 2 standard deviations above the mean. And we would go 76 minus 70, divide by 3, and we get the number of 2. If you remember back in February, I told you that when I teach statistics to my college students, I give them an extra credit assignment where I ask them to write personal ads where they describe their attributes using z-scores, and they have to prove that they actually posted it online in order to get the credit. And it makes for sort of funny reading. Like if you are tall and slender, you might say, well, my weight is a -1, but my height is a 1.5. Or if you think you're really, really funny, you might say, yeah, my sense of humor is a 3. And if you think you're beautiful, you might say, yeah, I'm definitely a solid 3. Because 3 standard deviations above the mean puts you in you're like 1 in 500 in terms of rarity. So anyway, z-scores are a really good way to look at any variable. And anyone who's taken a statistics course and has been inflicted with formulas for figuring out things like correlation coefficient, which we're about to do, you probably just remember horrible formulas, and there's no reason for that because it all has completely simple meaning using z-scores. And so let's move forward. So and that I just wanted to remind you again, z-scores with the standard deviation. So if you had a z-score of 3, you're all the way out here. You're above 99.7% of the population is within 3 standard deviations of the mean. So this means literally you are, 1.5 out of 1,000 is out here. So This is the same scatter plot of the college student's height and weight that you saw a few minutes ago, and it looks exactly the same. It looks exactly the same because all I did was I changed the scale and I changed the origin. So right now, here's 0, 0, and and there happens to be a person who is occupying 0, 0. This is a person whose height is average and whose weight is average. They are, Mr. Average. And everybody has been assigned their coordinates based on their z-score. So this person here has a z-score of 6 for weight because they are the standard deviation for the weights, I think, was like 20 pounds in this sample. So they were like 120 pounds above the average, and their height was less than 1 standard deviation, and that was about 3 inches or so. So they were about 2 inches above average in height, but they were about 120 pounds heavier than the average. So how do we decide how to kind of quantify association? Well, the idea is if we have a positive association, then we would tend to have, when we normalize it, we would tend to have the bigger the z-value for the x value, the bigger the z-value should be for the y. So we should have lots of things over in here, and we also should have lots of things in here because as the z-score for the x value gets negative, the z-score for the y value should get negative also. That would indicate a positive association. And so here's a really simple, almost too simple, but it works perfectly, simple way to compute it. What you do is you take every point, and we've already computed them to z-scores. We just take their x coordinate, which is a z-score, we take their y coordinate, which is a z-score, and we multiply them. In here, you're going to be multiplying positive times positive. In here, you're going to be multiplying negative times negative. Now look at something like this. What kind of a person is this? They are a weirdo, not in any way except for their height and weight doesn't seem to match what's going on with the rest. Oh, I'm getting some comments here. Let me look at the chat. Can I see it? Can you say where this data is from? It comes from various places, but when I make a summary document, I will give some sources. So, okay. So let's again look at this individual here. So because I know these are males, he is short and heavy. The trend should be the shorter you are, the lighter you are, which of course isn't always true. This person is a mild outlier. And if we take their x coordinate, it's negative because they're below mean in height. If we take their y coordinate, it's positive because they are above the mean in height. And so this would end up being a negative number. In fact, every single thing in this quadrant is going to be negative. And likewise, every single thing in here is going to be negative as well. So like this person here, they are a tall person, but they are relatively light. And so their height is going to be a positive z-score, but their weight is going to be a negative z-score. So all the things in here, when you multiply the x and y coordinates, they'll be negative, and all the things in here, they'll be negative. But here they'll be positive, and here they'll be positive, and they'll be more positive the further out you go to here, or the further out you go to there. And so if you add all that up, you should be able to get a measurement of something. And in fact, it's called the Pearson product moment correlation coefficient, which everyone just calls correlation, and they usually call it capital R, and not to be confused with the statistics computer programming platform, which is also called R. But and the way you do it is you take each point in the scatter plot, you multiply the z-scores of the x and y coordinates, you add them up, and then you divide by the number. You take the average. That's what this number is. Okay. So again, going back to the picture, it's the average of the products of all the points in here once you've normalized it. And it's an easy thing to do with a computer. Takes you know, a zillionth of a second. And what you get is something, it's not trivial, but it never is bigger than 1 and it's never less than -1. If it's exactly equal to 1 or exactly equal to -1, then it means the scatter plot is exactly on a straight line. If it's +1, it's going to be a straight line with a positive slope. And if it's -1, it's going to be a straight line with a negative slope. And when it's close to 1 or -1, then you will generally get, the association will be generally very strongly positive or very strongly negative. But there's some caveats. When R is close to 0, that means that that you have things in the plus plus quadrant and the minus plus quadrant and the minus minus quadrant and the minus plus quadrant. They're all kind of canceling each other out. So you basically have a cloud of points, and usually there's no association between the variables, but not always. Again, there's a caveat. And so let me show you some pictures to sort of build your intuition about what various values of R are. And then I'm going to look at some computer outputs that will annoy you. Okay, so back to our young adult males, and the value of R is about 1/2. So it's positive, and it means that there's a positive association that, and in other words, what's being said in some sense is the taller you are, the heavier you are, and oh, somebody asked, is there a difference between lowercase r and uppercase r? No. So sometimes you use a lowercase r. The capital R does refer to the computer programming platform. So, okay. This one, you can see the R is quite close to 1. And that it makes sense that the R is bigger, that the correlation coefficient is bigger. And now remember the one about absences versus final exam. The correlation coefficient isn't 0. It's not terribly big, but it's negative. So what is this saying? And I would love it if somebody just spoke up. What does it mean in terms of what it's saying about school? You could either say it with chat or say it with a voice.
So it seems to be saying that there's a slight negative, very slight negative relationship, saying that the more you're there, the lower your final exam scores are.
Exactly. Yeah. And now if you just look at the scatter plot, I mean, the naked eye, you really can't tell. But if you sit there really carefully, you can do the following, and you can agree with this. So when I computed this, I said, really? I didn't notice it, but then I said, oh yeah. The way I thought of it is I took the goody goodies here, the ones who are getting the perfect attendance award, and I worked out their average on the final. And their average, I forget, the average final exam score I think was about 11. So this was like a hard math class or just a hard final. But the average of the people who had no absences was higher. It was about 12.5. So it wasn't a lot higher, but it was definitely higher. In other words, you could say if you were not absent at all, you got above, on average, you did better than the class average. And if you continue looking at these vertical lines, it's not exact, but if we take each vertical line and tell a story about it, what you generally see is lower outcomes. Not completely. For example, this person here did quite poorly, but then this person was absent more but did better. And this person here did just as well, and they were absent, quite a bit more, and so on. But if you slice the data like that, you do get a vague sense of it. But still, the fact that this is a number computed to so many decimal points, what does it really mean? And we'll look at, when we look at regression lines, we'll get another idea about what this is. Okay, so what are some of the problems with R? And we're going to switch to a different screen picture in just a moment. But with the way it's computed, it's very sensitive to outliers. In other words, to data points that are far away from average behavior. And not only that, if you have a data point that's an error, that can really mess up your R. And data points that are errors are quite common. If you think about it, how is data collected? If it's not collected by machines, it's collected and typed by people. Who are these people? They are people with really lousy jobs. And these are people who are not necessarily take pride in quality control. I know this for a fact because my first college job, many years ago, was doing data entry for an observatory. And I got paid so little and the job was so boring that every once in a while I would just type in random junk because, I wasn't getting paid enough to do a good job. I'm ashamed to admit it, but, I don't think I caused any spaceships to crash. But so data's filled with noise and errors, and a large part of handling data has to be getting rid of the weird data. And there's lots of sophisticated ways of doing that. But if you're not sophisticated about it and you just sort of plug things into a computer, you often will get R's that make no sense. And I'll show you with some data in just a few minutes. And it also may not capture phenomena that aren't linear. And again, we'll take a look at that. And then there's then this is leaving the world of math behind, but very important when you're hearing people talk about statistics, and often people will say, well, this is very strongly correlated with this. And most of the time when somebody says this, it's complete nonsense. Or if it's not complete nonsense, it is certainly not a definitive statement. And if you haven't done this parlor game of coming up with things that have strong R's, but have absolutely no causal nature to them, here, so unlike say height and weight, it seems plausible that if somebody said, I'd like to introduce you to my friend Joe, and my friend Joe is 2 meters tall, and you know nothing at all about Joe other than that he's 2 meters high, you would expect that he's heavier than average. That is a completely rational thing to expect, okay? And you know that because you sort of know how human bodies are created, but because you have sort of a causal idea here. But here are examples of some of, and I'm sure you have your favorite examples. I think I have 3 here. If you look at if you do a scatter plot of time of carbon dioxide levels and frequency of obesity in the United States, you see something which indicates that perhaps extra CO2 is causing people to gain weight. And of course, what's happening is that there's some confounding variable, which is that as time passes, for some reason, Americans are getting more obese, and as time passes, also CO2 levels are going up. There's no causation at all, and so computing an R for this is an incorrect use of statistics. And then the favorite one that we use in all of our statistics classes is looking at different days of the week, different days of a year, and looking at how much ice cream is sold and how many people die of drowning. And again, you could say, oh, ice cream seems to be a risk factor, and if you eat ice cream, you might drown. But no, you eat ice cream in the summer when people are swimming, and when people swim, some people get unlucky. And there is a group called the I forget their name. It's like pirates. It's like Rastafarian, but with pirates, like piratarians that advocate piracy. It's just a joke, but they explain that piracy is a good thing because the less piracy there is, the more global warming there seems to be. And so probably piracy, the more piracy you have, perhaps the global warming would diminish. So that's a very nice idea, but I don't think it's true. Okay, I'm going to switch to a Google sheet. Let me see if I can find it. And there it is.
And we've
Okay.
got the survey has just popped up. If everyone wants to quickly answer that, it would be
Okay. I just closed my survey because it got in front of my screen, but I'm not sure how it works for other people. So this is a Google Doc, which and it's one that I gave the link to everybody. And at the my last slide, I have the links, and so you can take a screenshot of that. So that you can go to this and play around on your own. And I have a lot of different tabs in there. Maybe about 20 by now. So it includes some of the raw data that you can try to play with on your own. There's this biology data. It has like heights and weights of all kinds of I think of these are just male students, and and then there's the college data. But right now I want to focus on random data for a moment. And so what I did was I made a table of two variables, X and Y, and X is just numbers from 1 to 100. And so there's the X axis. And the Y values, I used a random number generator, which we talked about in previous meetings. If you look at the code for it, there's the code. It says just take, actually, no, that's the prediction, sorry. I take a random number, multiply it by 50, a random number between 0 and 1, and then I add 30 to it. So this is going to be, the output's going to be a number between 30 and 80, and they're all equally likely. And so there's no rhyme or reason to my XY data. X goes from 1 to 100, and Y is just a random number from 30 to 80. So you would expect the value of the correlation coefficient R to be close to 0, and indeed it is. And if you just hit the delete key on a blank cell, you can make the random computation repeat itself. And so you can see the R keeps changing, but it stays close to 0. Now there's that red line, which we'll talk about. It's the trend line, or the least squares regression line. We'll talk about it in a little bit, but ignore it for the time being. Anyway, this is completely random data, and it makes sense that the correlation coefficient should be 0, because after all, any knowledge about X gives you no knowledge about Y. Okay, the fact that X is 50 or the fact that X is 75 won't tell you anything. You won't have any inclination about anything that could be different about the Y value. But what if I were to take some of these values here and just make them be zeros? And what I want you to do is keep track of R. I'm going to just take the first 10, make them zeros. Notice what happened to R. It jumped up to 0.4. Okay. And I'm going to do something even worse. I'm going to make this Y be, say, negative 100. And I'm going to go down to some of these big values and make them big, just a few of them. I'll make this be 100, and I'll make those 100, and I'll make these 200. All right, so what we have is a cloud of junk, random junk, and then we have some big values and then some really big values, and suddenly we got a correlation coefficient that's saying we have a pretty good association. But really, we just have like nonsense numbers in here, okay? And now here's an even worse one. Look at this data, okay? When you compute the value of R, you get a low number, which would, and so if somebody did not make a graph of this and they just had the numbers, they'd say, well, there's really there's not really much association between the X variable and the Y variable, when in fact, the X value gives you a precise prediction of the y value, because what it is, it's a trigonometric function. I'm actually using the cosine function, but it's showing that whatever x is, it's sort of modeling sort of like a spring going up and down. Okay. And so nonlinear data is very poorly served by the correlation coefficient, and there's no reason necessarily to expect that data is going to be linear. Sometimes it is, and sometimes it isn't. And so a lot of people who say there's very little correlation between this or that, they might be completely missing a very strong association between variables. You wouldn't want to say that x and y are positively associated here, but you definitely you definitely would want. Oh, is the poll window getting in the way? Because I closed my poll window.
You can just move it over.
Oh yeah, okay, that's to everybody. Right, yeah. So everybody can move it away. Yeah. So so again, the association, you wouldn't say there's a positive association or a negative association, but you would say there's a rock solid association, in that, in other words, there's a total predictability between x and y. Okay, complete predictability. Okay, so I'll be returning to these sheets in a moment, but I think I want to go back to my slides now, and I think I can do that here. There we go. Good. Okay. Before I go any further, because I want to talk about regression lines. Do you have any questions about correlation coefficient? So let me just pause for a minute or two. It's funny, you know, when somebody talks, I can hear you. And so someone named Jerry said, but he didn't ask a question.
Sorry, that was me.
That's okay.
I do not have a question.
Okay.
But this is great. Thank you.
Well, you're very welcome. I'm happy to be here. I wish I could be with you all in person somewhere. But my guest bedroom is actually pretty nice.
I have a question.
Sure.
So when do we know? I think the thing is, you said like many times you feel that there is no correlation, but you find the R giving you a positive or negative correlation. So when do you figure out that the variable R can be used for these variables? Like when do you figure
right?
that out?
Yes, that's an excellent question, and you know I'll give you the short answer, but the long answer would be you hire a statistician who is skilled in both statistics and in communication, because it's definitely a science, but it's also an art, and a lot of it has to do with context and communication. But the simple answer is you look at the scatter plot, and for example, the scatter plot that we're staring at right now, it makes no sense to talk about both a value of R and the linear fit that we're about to do. Because what you can see is that it's mostly random, and the better way to describe it is to use words, which is to say people who don't miss any classes seem to do on average a little bit better than the average, but not a lot better, and that there's a fair amount of scatter, and the people who miss a lot of classes, none of them do particularly well. And that's about all you can say, because otherwise, you know, there's quite a bit of variation. And in fact, if you think about it, if you wanted to do good data presentation, like if I was a teacher and I wanted to convince my students scientifically that they should come to class, one thing I would do to make this graph easier to see would be to color code it, like say from red to green, where green are the higher grades and red are the lower grades, so that you could sort of see these grades. And then what you notice, better than a trend line and better than a value of R, you would notice that there's a little more green on the left than on the right, and there's more red on the right than on the left, just a little bit. and but it's not convincing, and honestly, this is really not the right kind of data for linear regression. One of the problems you get when you read statistics, like if you go to 538.com, which is an interesting website, they talk about statistics a lot, and they'll often say, we ran a regression, we had a model, and that they're doing more complicated things because they're using more than two variables. But often you don't see the raw data and you don't see the scatter plots, and so it's not always clear whether these models are making any sense. So it's a really excellent question. I see a question about R squared, and I will get to R squared. So yeah, R squared, I'll talk about that at the very end. Okay, so let's now look at this notion of lines to fit the data. And so the question is, what is the best linear fit to the data? And so there's three important words: linear, so we're restricting it to a straight line; best, how do we define best? And fit, how do we define fit? So best, and I implied it with my sort of slightly sadistic analogy of minimizing pain. But if you don't like minimizing pain, here's another way of thinking about it. What we're going to do is look at what's called the least squares regression line, here's another one you can see, and there it looks like it makes sense. Like if somebody said, if you had to draw a line, where would it go? You draw something like this. If you asked 10 people to draw the line, they'd all draw something close to this. If we did it with our young men of heights and weights, it would be harder to draw a line, but you would most likely draw a line that's going up rather than going down. Okay, and so here is a very simple explanation of what this line is. Okay, first of all, it was invented by Carl Gauss, who is one of the greatest mathematical minds to ever exist. Gauss's birthday is on the last day of this month, and so everyone should raise a toast to Carl Gauss on April 30th. I think he will be 243 years old on that day. And if I was at the Museum of Math, I would want to have a party on that day. It's as good as Pi Day. And Gauss invented it. Gauss was one of the first inventors of statistics. The normal distribution is also called the Gaussian distribution, and for good reason. And Gauss was he was investigating the motion of asteroids. The asteroid series had just been discovered, and with telescope observations, and it was very hard to see, and it got lost. Someone had seen it, they realized it was a new planetary body, they were able to make estimates about where it was located and how it was moving, but before they had more definitive knowledge, I think there was a storm or something, and it just disappeared from sight, and no one knew where it went. And Gauss took the measurements of where Ceres was, and he was able to make a prediction where you'd be able to see it next. And so he started, it was one of the first uses of the notion of sort of a best fit, and so it's an interesting historical epoch in math. So and I'm not going to show you a whole lot of formulas, although if we need to, we can go on the blackboard and look at some stuff. But the key thing about this regression line is it always passes through the center point. So it passes through the mean value of x and the point where the x coordinate is the mean value of the x data, and the y coordinate is the mean value of the y data. And you saw that with that normalized version of heights and weights. And so another way of thinking about it is if you just normalize your data, it goes through the origin, because 0 is going to be the mean. So the regression line always goes through the mean point, and if the data is normalized, it always goes through the origin. And the sum of the squares of the vertical distances from each point in your scatter plot to that line is the least possible value. And that's why it's called the least squares regression line. And a reason, here's a physics reason for it. If you were to imagine each point in your scatter plot dropping down to your candidate for a best fit line, if you dropped it down with a spring, and so you had springs dropping down from each scatter plot point to your candidate for a best fit line, and then you just let go and you waited for that line to stabilize, it will stabilize in the position of least energy, and it will be the what is mathematically called the regression line. And so and if you don't like squares because you wonder why squares, we sort of talked about squares, a couple of weeks or a couple of months ago. The reason you do squares is partly because squaring turns negatives into positives, so you don't have positive deviations and negative deviations canceling each other out. But also when you add up squares of deviations, you get what's called the variance, which is the square of the standard deviation. And this was a sort of a mathematical fine point, which I mentioned a few months ago. Variance adds. If you have two different random variables, the variance of the sum of them is the sum of the variances. So variance behaves really well mathematically. It turns out that computing these squares helps a lot. It doesn't help the intuition of a human brain, but it works very well with mathematics. And I'm sorry I can't give you a better a better sense of it than that. But if you think about this sort of physics notion and also the idea that so the error is the distance from your best fit line to your actual value, that's what's going to be minimized. So let's go back and look at a picture. And let's look at this picture here because the data is a little nastier compared to that picture. So if you look at say you ask yourself, well, suppose you remember the question that I asked. I think you are you're going to you want to predict the weight of somebody who is 6'2" tall. Well, in our actual data, there's only 2 people and they seem to be a little bit underweight, but that doesn't really matter. The best prediction in general would be the value on the fit line at 74, which would correspond approximately to 200 pounds. And so if you said a 6'2" person is 200 pounds, you're not always going to be right. Likewise, if you said a 6 foot tall person is 179 pounds, you wouldn't always be right. This person is underweight, this person is overweight. You have a whole spread of people, but still overall it's going to be the best guess. And if you were to make all of these guesses and you're figuring out what's the aggregate least square error that you'd get, it would be found by fitting the line here. Now you might say, this is crazy. This has nothing to do with the real world. It's just a mathematical formalism. And the answer is you're absolutely right. Eyeballing a best fit line would be almost as good as well. The question is, what's the purpose of the line? Okay. And that's where you can get into some real difficulties, because there's lots of ways of misusing statistics. Oh, I noticed somebody pointed out that Gauss's age will be a power of 3. And as long as we're being nerdy about this, I have to share with you that when I first started working at the University of San Francisco, we lived on 27th Avenue in the Richmond district of San Francisco, but we lived at 243 27th Avenue, and we lived in apartment 3. And so my address was 243 27th Avenue, apartment 3. And so I thought it was, you know, a good omen that it was all powers of 3. So Gauss would have approved, I'm sure. Okay. So that's where this line comes from. Okay, how it's computed, the details of that in many ways are unimportant. But I think the best way to think of it is to internalize this physics idea of least energy. So imagine you have springs dropping down onto the fit line, and the fit line will stabilize when the energy is minimized, when everything balances. And as you might remember from your physics classes, the spring energy is proportional to the square of the stretch. It's not a linear function. The force is linear, but the total amount of energy to pull it out is proportional to the square. So that's where this least squares comes from. Okay. And so now we're going to end with cautionary tales and some loose ends. And so first, the cautionary tale, which is a famous sequence of 4 scatter plots. They're very simple. They each have 11 dots in them. And they're called Anscombe's quartet, because they were invented by a statistician named Anscombe, and it was just done in the 1970s. And what's amazing about these data sets is that for each of them, let's look at this one, because this is the only good one. For this data set, the mean value of X, I believe, is 11, and the mean value of Y is like 9. In fact, I know that because it's going right through there. And we have a regression line with a slope of 3, I believe. Oh, no, slope of 1/2 and an intercept of 3. It's the line y equals 0.5x plus 3. And so it's furthermore, the standard deviation of the x variables and the standard deviation of the y variables, we can compute them. I forget what the exact numbers are. But with this data set, you have the same mean and the same standard deviation. Same mean, same standard deviation, same R. And the value of R is about 0.8 in all of these. You have the same value of R, which is, I think, 0.82 approximately. And so if you just looked at this and somebody said, yeah, here we have a scatter plot and the correlation is 0.82, you would, and if you didn't have a picture of it, you'd say, oh yeah, well, that's probably, you know, a positive association. It's close to a linear relationship. And sure enough, it really is. There's, you know, there's a little bit of wiggle in the data, but it looks okay. If that's all you had, you'd say, oh yeah, it's kind of similar to the one with the grade on the midterm versus the grade on the final. It seems like you have a good knowledge about X1 gives you fairly reliable knowledge about Y1, right? If you know that X1 is 14, you would probably be predicting that Y is about 10. And you might even want to go out on a limb and say, I bet I know what would happen if X is 18. I bet Y would be about 12. That would be an honest kind of prediction. But if you look at the data set X2, obviously it's a nonlinear thing. It's just a parabolic motion, but we end up getting exactly the same R and exactly the same standard deviation for Y, exactly the same standard deviation for X, and so on. And then if you look at this one, what's going on here is that clearly the trend line should be this line, but what we have is just a weird outlier. It might even just be a typo or you know, an underpaid college student who's maliciously sabotaging data. And so clearly this least fit line is mathematically the correct least fit line, but if you asked any elementary school student to draw a best fit line, she would draw this line and she would be correct. And then if you look at this data, this is complete nonsense. There's no linear nature to this at all. What you have is a weird outlier, and then you have all you know is that X is basically always equal to 8 and Y is all over the place. there's no sense of a linear association. The variables are completely crazy. But if you were to blindly just do a computation, you would say, we have we can predict that when x is 14, y should equal 10. Whereas in the real world of this variable, x is only equal to 8, and this is probably a typo. Okay, and so what you want to take from this is not that R is bad, not that linear regression is bad. It's good as long as you draw your scatter plot and you think about what you're trying to do. Okay, and so and here's a couple of loose ends. So someone asked about the role of R squared, and I'm curious. I wonder if I can see this with. Can I get the hand raises? I'm not sure how that works. I'm not sure I can see hand raises, but I'm curious how many people have heard of R squared. Oh yeah, I'm seeing hands going up. This is great. I see 1, 2, 3, 3 or so people. And so 4 or 5. So, you know, a modest number of you have heard of R squared. And the place where you will hear about R squared, and I'm not going to give you a very technical answer. You can go on Wikipedia if you wish and just look up the coefficient of determination and you'll get equations galore. But the idea of the R squared is, well, one, it's just the square of the correlation coefficient. And remember, the correlation coefficient is going to be a number that's less than 1 in absolute value. So if it's, say, 0.7, which is a fairly large number, it's a bit closer to 1 than not to 1. When you square 0.7, you get 0.49, which is about 1/2. And 1/2 is sort of suddenly a more modest number. When you have a correlation of 0.7, the square, the R squared, is about 50%, 0.5. And it's called the coefficient of determination, and its technical definition is, and this is something that seems almost mystical, and it gets misused. It says that 50% of the variance in the response variable can be explained by the explanatory variable. Okay, so let's go back and look at a picture of this with so here is the height and weight one, and the R squared was the equation for the regression line was outputted, and your Google thing can do this very easily. I can show you how if you wish, but it's not that important. It's an easy enough thing to look up, and you see it in some of the graphs which you'll have access to. The R squared is about 25%, and so what it's saying is that so let's think about the most naive thing you could do. Suppose you had no regression line at all. All you knew were means. And so you knew that the mean weight of the mean weight of a male was about 180 pounds. And so suppose I said, hey, we have this guy, he's 6'2". Can you guess his weight? And you'd say, well, I have no information. I'm just going to guess his weight is the mean weight of a male, which is 180 pounds. And you would say that for no matter what I asked you. If I said, I have a 64-inch tall man, I have a 69-inch tall man, I have a 3-inch tall man, you would say the same thing, 180 pounds, 180 pounds. In other words, you are you have no knowledge at all. And so what's happening is the actual answers of the collective, if I were to collectively ask you about every single person, your collective answers would all be 180 pounds. And so what would happen is the actual answers would be deviating from 180 pounds. The variance of that would be the full variance of the weight of the population. And so if you were to merely guess, if you were to merely guess 180 pounds, then all of the variation of the weights, which is the response variable, all of that variation, you're not losing any of that variation. In other words, you're not explaining any of it. On the other hand, if I use the trend line as my answer, so then for a 66-inch person, I wouldn't say that he's 180 pounds. I'd say he's 150 pounds. And for 76-inch persons, I would say that they're about 215 pounds. If you use the trend line prediction, and then you do that for everybody, and you collectively say, what's the variation now, which is the error variation, the sum of the squares of those errors, it's going to be smaller. And what is it as a fraction of the errors if you knew nothing, which would be the total variation. And so what this is computing literally is if I were to do this trend line prediction for every single data point in my data set, and then work out the square error from that prediction, it would be about 24% as big as the actual variation of all of the population from its mean in weight. So when somebody says something along the lines of, well, you know, heredity only explains 50% of IQ, they are reading a statistics article and they're looking at an R-squared and they're not understanding what they're saying. Nothing explains anything. The accident of language is that the x-axis is called the explanatory variable. In other words, height is explaining weight. Height doesn't explain weight. Okay, heredity doesn't explain IQ. These things are very, very complicated, but that's what R-squared is measuring. And so I'm probably going to shut up about R-squared because I think if I keep talking, I'll just keep get more confusing. But I hope that helped a little bit. And then I have another loose end, which is the notion of extrapolation versus interpolation. And when you're using these regression lines, if you go past where the data is, and I did that with the first of the Anscombe quartet, you're always in danger of losing. Right, you're always in danger of leaving where the data makes any sense. Interpolation means you use the trend line inside your data zone, and that's generally safer as long as your data can roughly be quote unquote explained by the least fit line. And so, and of course, the last word on extrapolation and interpolation, I'm going to leave it to a more eloquent person, and many of you've probably seen. This isn't the quote, but this is an example of people that are using interpolation, and they're using it as a fact rather than as something that comes with an R-squared. Okay, so I picked this off the internet. It was from an ad for like some sort of exercise equipment, and and they had a footnote. It was some medical study. It had a trend line. We have no idea what the R-squared is. We have no idea if the data was linear, and we have no idea really what's meant by every hour you sit. We know what life expectancy is, but you get this scary thing. Every hour you sit, your life expectancy drops by 22 minutes. Okay. That's an example of interpolation, which may be true, may not be true. Another example is one I remember when I was when my son, who's now in his 20s, when it was his second birthday, my mother-in-law called us up to say, to wish him a happy birthday, and she said, if you double his height, you'll know his adult height. And I said, that makes no sense. And she said, no, it's true. And now my mother-in-law won the math award at Iowa State University. She should have known better. What she should have said is, well, it's what the trend line says. But the truth is, if you take your height when you're 2 years, if you did a scatter plot of height on your second birthday and height when you are an adult, you're not going to get a straight line with a slope of 2. You're going to get a scatter plot that will have some noise in it, and it might have a slope of 2. and so certainly the best prediction is to double the height, but there's going to be some error. And so, you know, what I said to my mother-in-law was, well, I'm sure that that my son's adult height is a random variable that's normally distributed, and the mean is twice his height today, but I don't know what the standard deviation is. I have no idea how tall he'll be. But now I'm going to go to the final the last word, and this is a famous quote of Mark Twain. And so I'll read it out loud, and I hope some of you have already read Life on the Mississippi. It's a great book. In the space of 100, it was written in the 1884, I think. In the space of 176 years, the lower Mississippi has shortened itself 242 miles. That is an average of a trifle over 1.33 miles per year. Therefore, any calm person who is not blind or idiotic can see that in the old Oolitic Silurian period, just 1 million years ago next November, the lower Mississippi was upwards of 1,300,000 miles long and stuck out over the Gulf of Mexico like a fishing pole. And by the same token, any person can see that 742 years from now, the lower Mississippi will be only 1.75 miles long, and Cairo, Illinois, and New Orleans will have joined their streets together and be plodding comfortably along under a single mayor and a mutual board of aldermen. There's something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact. And certainly Mark Twain couldn't have, you know, I can't say it any better than Mark Twain, so I'm going to end with that. But we do have time for, you know, a couple of questions. So, so unmute yourselves, please. So Top Beagle or Louisa, anyone want to ask a question? Is it being chatted? No.
All right, I'll ask the question.
Sure.
So how tall did your son end up being? Like, was it anywhere close to what your mother-in-law said?
I knew you were going to ask that. And, you know, the sad thing is I don't remember exactly how tall he was when he was 2 years old, but he ended up being taller than you'd expect. And I know this because I can do science to some degree because I'm married to an identical triplet. And one of my sisters-in-laws, she had 2 sons, and the father was about 6'6", and I'm about 5'8", and my son is taller than one of those kids, you know, and they're both fully grown. And so my son's about 6'1", so he's a little taller than you'd expect. So basically, I would say he's about 1 standard deviation taller than the mean height that a male child of my wife and I would have. So like if we had 1,000 children, my son would be in the top 14th percentile of those he'd be among 140 kids that were taller than average. That's the nerdy answer to your question. Another question?
There's a question in the chat.
Oh, okay. Would you please show the first Wikipedia quote near the beginning of the presentation? Oh, about the definition of statistics? My pleasure. Hold on a second. And oh, and I will also show you the last slide because that's important. So that's a definition of statistics there. And there's the question, can you say again how you would explain R squared? And my answer is no, it'll take too long. I'm sorry. R squared is a complicated, is really a complicated thing. But my best advice to you about R squared is if somebody says something explains only some so-and-so percent of something else, As soon as you hear the word explain, your hackles should go up and you should ask them, what do you mean by explain? And if they cannot explain that to you, then you should not listen to them that much. You should go back and read the actual data or look at the article. But here is my email, and feel free to contact me anytime. And, you know, I might not write back immediately, but I'll read what you write. And then this is the Google spreadsheet, which you can just play with. You only, I think, get viewing rights to it, but then what you do is you can make a copy and then you can edit your own. And then likewise, in some of the previous sessions, I had workbooks that use a very powerful Python-based computing platform, and I've included some statistical plots in there that you might want to take a look at. And so if you are a little more nerdy, then this is something you might want to take a look at. Okay, so it was really nice. I'm sorry I couldn't see you folks in person and vice versa, but I hope everyone is staying healthy and sane. And I look forward to the next time we can get together. So thank you very much, and take care. Take good care of each other. Bye-bye.
Bye. Thank you very much.
Bye. You're very welcome. So bye-bye, everybody.